of the use of performance-enhancing drugs in professional sports? Good thing or bad thing? Yeah, what do you think?
I think it depends. Like, there's like steroids, not just for performance, but also for like health issues. So I feel like it depends.
Okay, very good. So we can medicinally use hormones, right, and steroids. So I'm super allergic to poison oak and poison ivy. And one time I got it really bad when I was growing up in California. And my doctor prescribed a corticosteroid. It's a variant of the cortisol molecule. And it helped clear up my my poison oak. However, corticosteroids are very, very different than anabolic steroids, right? And anabolic steroids get closer to the use of like human growth hormone and things like that, that artificially allow us to increase muscle mass. So what do you think? Specifically with respect to professional sports, anabolic steroids, good or bad? Yeah, Carly, what do you think?
I think that the anabolic steroids, they are used in the sports section a lot. That's why a lot of times they're banned, because a lot of people overuse them and they do harmful things to their bodies because they're overusing the steroids, trying to get that edge over something.
I love it. And so currently, particularly within like US sports, right, there's a ban on performance-enhancing substances, including anabolic steroids. So because there is a ban, people acquire them illicitly and they use them. But what if we just said, do it if you want to do it? I mean, let's remove the ban, and if you want to use an anabolic steroid, you go ahead and use an anabolic steroid. And the reason that I suggest that is, I was watching this documentary about anabolic steroids, and I'm not advocating the use of anabolic steroids, but it made me think a little bit differently about them. And one of the statistics that was cited in this documentary was over 90% of all professional athletes use some sort of performance-enhancing substance, which is a crazy statistic, right? So why not just remove the ban and say, if you want to do it, do it.
It's kind of like saying the thing with like illegal drugs. Just be like, if you want to do meth, go ahead, do it.
Exactly. It's exactly the same thing as that. Is that good or bad?
It's pretty bad.
Yeah.
Why is it bad? So really, what's the difference then between like methamphetamines, opiates, which are prescribed, marijuana, which has become legal in many states, and alcohol or tobacco? Yeah.
Is it because when you come off of a steroid or even drugs in general, you're not on that high anymore. You're in a state where you're coming off the drug, so
Withdrawals.
yeah, that's what it's called. Thank you.
Do I need to withdraw?
Withdrawal, yeah.
Sure. Do you feel like similar things happen with alcohol?
Yeah.
Don't you feel like there's this weird double standard in our society? Like, some drugs are okay, but other drugs aren't. And really, where do we draw that line? There's this contemporary folk singer named Todd Schneider. He's really, really good. And he has this really funny song in which he says, it doesn't matter which drugs you're using, but whose drugs you're using. And it's pretty true, isn't it? Because, I mean, think about this. We've only recently begun prescribing like THC and marijuana derivatives, but we've been using opiates for a really long time, like cocaine and heroin and things like that. In fact, you can still get opiate derivatives. If you've taken hydrocodone or Oxycontin, those are all opiates. And opiates are way more addictive than THC. Now, I will say this again, I'm not advocating the use of any of the substances. I don't use them. I think you don't need them. But it's an incredible double standard. We've gotten to this place in professional sporting goods, and I know I'm standing on a soapbox right now, but society is really driving this anabolic steroid problem. Because think about us as consumers and what it is we expect to see in sporting events, right? What we expect to see are home runs and grand slams, lots of touchdowns, way more soccer goals, things like that. I went to, so back in Texas, one of the field trips that the elementary school kids went on was to a minor league baseball game in Dallas. And I took my, I think she was 11 at the time, my 11-year-old on this field trip, and we sat through 7 innings of a minor league baseball game, and it was the most boring experience of my entire life. Across those 7 innings, not a single player got on base. It was terrible. The whole time I was thinking, why won't somebody take anabolic steroids and like, at least get on base? I'm just kidding, I wasn't really thinking that. But if you think about people like Barry Bonds and Mark McGwire and, you know, other huge baseball and football stars, they're paid to be excellent. And how is it that you achieve that excellence? Once your body is peaked, that's it. And so how do you increase the glass ceiling that is your biological potential? Anabolic steroids. One more question, then we'll move on. Fundamentally, what's the difference between a performance-enhancing drug and a performance-enhancing piece of equipment?
Doesn't.
Don't they both accomplish the same thing?
Yeah.
If you guys look at the advances in track and field, so we have people, crazy good people like Usain Bolt, right, who are just super fast. If you look at, and there are always new course records being set, new world records being set, but if you look at the actual biological prowess of individuals and compare that to the rate at which world records are being broken, there's a great disparity. Really, world records are being set not because athletes are becoming better athletes, but because the technology that they're using is becoming better. The technology of the track is better. Their shoes are better. The clothing that they wear is better. It's crazy. It's the same thing with swimming. Really, world records in swimming are being set because technology is advancing, not because people like Michael Phelps are inherently better than people 20 years ago. One last example. So are you guys familiar with Lance Armstrong? Crazy good athlete, right? I mean, the dude won the Tour de France like 6 times, which is insane. But they were all stripped from him because
He did a steroid. Didn't
Of
he
doping.
like do, yeah.
of doping, yeah, steroid use. But all of his competitors are also doping. The problem isn't who's doping, it's the kind of dope that you're using and how it's tested for and discovered. So let me give you, I think, 3 different scenarios. One of the type of doping that endurance athletes do is called blood doping. And blood doping is where you artificially increase your number of red blood cells. And that's a good thing, right? Because red blood cells facilitate the transmission of oxygen. And so there are a few ways that you can artificially increase the number of red blood cells. The first of which is you can train at altitude. So if you go up to like 10,000 feet and you start doing aerobic things, your body is going to be oxygen deprived, and the physiological response is to produce more red blood cells. Secondly, you can sleep in an oxygen deprivation chamber. So you sleep in this little canister that restricts the flow of oxygen, and you're basically suffocating yourself throughout the night. And because you don't have as much oxygen available, your body naturally produces more red blood cells. The third option is you can donate blood months prior to your event, and then you can take a transfusion of your own blood and increase the number of red blood cells. So one of those is illegal, the other 2 are legal. The illegal one is
Last one.
transfusions. Doesn't that seem like an arbitrary thing? Totally
Mhm.
arbitrary.
Oh.
But yet,
Mhm.
that's the rule. Okay. Just one more time. Don't do drugs. Don't use steroids. You guys don't need that kind of stuff.
If I was an athlete, though.
All right. So we're going to move on to a third class of biologically important molecules. And those are the proteins.
You need something. Here's There's no way.
So the proteins are really like the workhorse of the cell. They do lots of really important things. So their function is first and foremost as enzymes. And an enzyme is a protein that catalyzes a chemical reaction. Chemical reactions commonly take a really long time. They're really, really slow. They'll happen spontaneously, but it takes a long time to do it, and it takes longer than our bodies need. So we have proteins that either speed up the rate of a reaction or they slow down the rate of a reaction. They're also important for transportation. Transportation, when we're moving one substance from one part of the cell to another, that's accomplished by a protein. Or if we want water to come into our cells, the cell membrane is going to naturally keep that out, right, because of that hydrophobic core. We have special protein channels, they're like little pores, that allow water to move freely into or out of the cell. It's called an aquapore. So these facilitate transportation as well. They're also really important for structure. And here you need to think about muscles, right? Our muscles are almost entirely protein. And then they're also important for defense. So when a bee stings you, or a wasp stings you, it hurts not because the size of the sting is large, but because of the venom that they're injecting into you. It carries a protein, and that protein causes pain. And so they're also defensive structures. Okay. The monomer of a protein is an amino acid. And the bond that we form between two adjacent amino acids is called a peptide bond. So the basic structure of an amino acid is this. There is a central carbon, and that central carbon is attached to a functional side group, is what it's called. We're just going to call that R for right now. Now this functional side group can consist of any number of things. It can be really small and boring like an OH group. It can include sulfur compounds, it can include phosphorus compounds or nitrogen compounds. But it's this functional side group that gives each amino acid its own identity. The rest of the amino acid is identical between aminos. So that carbon is also attached to a hydrogen. And then on one side, it's attached to a carboxyl group, or carbonyl group, which is double bond. A carbon is double bonded to an oxygen like that, and then an oxygen and a hydrogen like that. The other side of this carbon is attached to the amine group. And the amine group is a nitrogen attached to two hydrogens, like that. So that's an amino acid. Now we could take that amino acid and we can do dehydration synthesis to attach two amino acids together. So if you were to attach those two amino acids together through dehydration synthesis, how would you do it?
Take the OH and then the H.
Yeah, that's an easy one, right? You take the OH off and the H off, and those are going to make a water molecule, and then we're going to attach this carbon to that nitrogen. And that bond right there called a peptide bond. So that functional side group, that R, that's what gives the amino acid its identity. It also determines how it is that amino acids interact with each other in a three-dimensional context. Yeah, Adam.
So, going back to this, those are two amino acids, correct? And amino acids, when they
1 and 2. Yep.
they create peptide bonds.
Mm-hmm.
Okay.
Yep. So dehydration synthesis occurs right here, and then we connect that carbon to that nitrogen. That bond is called a peptide bond. Yeah, Carly.
So if you were to have us draw this kind of bond after dehydration synthesis, we would take out the OH and the H, and that would be one molecule up top, and then you would just connect the C.
Perfect. Okay, so these functional side groups determine how it is in a three-dimensional space amino acids are going to interact with each other. Now, by far, the most important characteristic of any protein is its three-dimensional shape. Its three-dimensional shape determines its biological functionality. And we'll talk about really quickly how it is we arrive at that three-dimensional shape. So the bond is a peptide bond. Now, we need to draw an important distinction really quickly. So a long line of amino acids that are all connected, that's the polymer, and it's called a polypeptide. So a string of amino acids is a polypeptide. Once that polypeptide assumes its three-dimensional shape, then it's a protein. So the difference between polypeptide and protein is three-dimensional shape. Okay, so there are 4 levels of protein structure that I'll want you to be familiar with for the exam. And they're really hierarchical. So, do you guys know what doilies are? You guys know what a doily is? So for those of you who don't know what a doily is, it's that